one last example of the mean value theorem, this one's actually a little bit easier than the previous one, is that we have this polynomial function, f at x equals x cubed, and we have an interval -5 to +5. And we just want to see whether the conclusion for C holds true for the mean value theorem on this interval. So first thing we need, conditions. Condition 1 is continuous. So is f equal x cubed continuous on -5 to 5? And yes, f is a polynomial. All right, so that's good. And right away, because it's a polynomial, we know it's easily differentiable. Okay, so the other question is f equal x cubed differentiable on -5 to 5? Okay, and the same answer, yes, f is a polynomial. So that's good. And so what we're saying is that there is some place where f prime at c is going to be equal to the secant slope. And remember our formula for our secant slope, y2 minus y1 divided by x2 minus x1, where f at b minus f at a equals b minus a. So our derivative is ridiculously easy. All right, so derivative of f at x is going to be 3x squared. And f at b is going to be, now remember, b in this case is going to be 5, a is going to be -5. So we're going to have 5 to the third minus -5 to the third divided by 5 minus a minus 5. Right? And we know the denominator is going to be 10 easily. Right? So we get 3x squared is equal to something over 10. And this is going to be 125 and 125. That should be 250. Or that's just going to turn into 25. But let's just verify that value. Okay, let's just go into our calculator, and we're going to take 5 cubed minus a -5 cubed. Right, and that should be 250, which it is. We divide it by 10, and that's going to give us 25. All right, so that's pretty easy. So we get 3x squared is equal to 25. X squared is going to be 25 thirds, and then we're just going to take the square root of that. Okay, so x is going to be equal to not just 25 thirds, but plus or minus square root of 25 thirds. And of course, we want to simplify this. All right, and so this one's a little bit sneaky, so we need to make sure we simplify it completely. All right, so another way we can write this is the square root of 25 over the square root of 3. Okay, so let's go back to our algebra 2, which is really the same thing as 5 over root 3. All right, but my math lab might not like that answer because we have to rationalize it. And you might remember from algebra 2 that to rationalize something, you just multiply the top and the bottom by the exact same thing that's in the original denominator. So 5 over root 3, we're going to multiply that by root 3 over root 3. And what does that end up giving us? Well, x is going to be plus or minus 5 roots of 3 over 3. Because remember, when you multiply root 3 by root 3, that just turns into 3, and 5 roots of 3 can't be multiplied out. Now, one last thing is we need to make sure that both of these values, okay, are they in the interval -5 to +5? That's the question. All right, we don't know. So let's go into our calculator. We're going to approximate it before we give a final answer to this. So we're going to say 5 roots of 3 divided by 3, and 2.887 if we were to approximate that. And clearly both of those numbers are between -5 and 5. So that's good. So this is one where we actually get 2 solutions. And so the 2 values that are going to satisfy this are going to be 5 roots of 3 divided by 3 plus or minus. All right. So hopefully that gives you an overview of both Rolle's theorem as well as the mean value theorem, what they mean geometrically, and then also what that means analytically to be able to find these. In the next section, we're going to take a look at one last application of derivatives to the graphs of functions, and that's going to be able to determine where functions are increasing and decreasing, and then secondly, how to determine the intervals of concavity for a